Okay, next let's look at simple linear regression. Simple linear regression is where we're predicting the output, the quantitative response, or the target, y, using just a single predictor variable. So this assumes, of course, that there is a linear or approximately a linear relationship between x and y. And this is the form that this equation is going to take if we're doing simple linear regression. So we're saying that y is approximately beta 0 plus beta 1 times x. In the case of the advertising data, we might examine the following linear model. We might suggest that sales can be approximated by beta 0 plus beta 1 times the TV spending. So you might recall this form from your earlier education as the slope-intercept equation, where we say that y is equal to some slope times x plus an intercept. So beta 0 and beta 1 as a whole are the coefficients or the parameters of the linear model that's generated by the linear regression process. We'll often refer to this model as y hat, so that y hat equals beta hat 0 plus beta hat 1x. And this is the useful output of a linear regression. So the reason we're putting a hat here is because that y is only being approximated. We can't know the actual model. We're putting a hat here because this is our approximation. We know that these are approximations. So our challenge is to find these coefficients, these best estimates. The process of linear regression is something that we can use to find these coefficients, and we do this using the input data, the data that we have. So in the simple linear regression case, this is these x and y pairs, which are the measured or observed data. So let's look at this advertising data set. Again, I'm going to load in my Python libraries here for examining this. I'm going to load the CSV. And I'm just going to look at, this is just simple linear regression, so I'm just going to look at two variables. I'm just going to look at the TV and TV spending and see how it's going to affect sales. So this is what the data looks like. I'm using .head just to show the first 5 rows. So you can see it's just XY pairs, but we have just TV spending and sales for our data, for our input here. The goal is to use this data to obtain the best estimates, beta 0 and beta 1, so that the linear model we generate with them best fits the data. And the most common way to do this is using the method of least squares. So if we're going to understand the method of least squares, it's important to begin with the concept of residuals. So the residuals of a linear model are the differences between the observed or the measured values in the data set, the actual values, and the value predicted by the model. So I think it's going to help actually if we get a visual of this. So I'm going to generate a simple linear regression model using scikit-learn. And you might notice that I've had to do a little bit of wackiness right here. The difference between TV and TVR is that TVR is actually an array, a single column array of data, and the reason for this is because this is what a scikit-learn model expects. It expects an array as the input and a column, just a column of data as the target. So I've actually had to specify that this as an array, even if it is just a single column array. All right, let's plot this. Let's plot the linear model and the residuals. And you can see here they are. So the red line is the linear model. That's the predicted, that's the line of best fit. The blue points are the original data, the data we were given. And these residuals are all of these lines in between the predicted line and the data. So what we're trying to do when we make this linear model is find the line that goes through here that has the smallest residual values overall as a whole. So one particular value might be small, but as a whole we want the smallest possible values, and this is going to be the line of best fit. So again, the method of least squares finds the beta 0 and the beta 1 by minimizing the sum of the square of these residuals. So previously we're looking at this and I'm saying we want, it's okay if this one's big, but as long as overall they're small. So we're actually not looking at just the values themselves. We're looking at the sum of these squared values. So there's an advantage to doing this. There's an advantage to squaring the residuals. So one, it removes the sign, right? A negative error or a positive error is not going to matter. If I'm including negative errors and positive errors, they might offset each other. So we don't want that. A negative error is just as bad as a positive error, and we don't want them canceling each other out. The other thing it's going to do is it's going to penalize large errors and tolerate small errors. So an error of 100 when we square it becomes, an error of 10 when we square it becomes an error of 100. An error of 0.1 becomes an error of 0.01. So in this case, we're penalizing it more for a large error of 10, but we're saying an error of 0.1 we're tolerating that. So the squaring is going to amplify the largeness and minimize the smallness. So what we're looking at is this error as a whole, and the way we're going to do this is through this idea of a residual sum of squares, so an RSS. And the RSS is, you can see we're squaring each of these errors. So we're squaring each error over each of the n points in the data set, and we're adding up that total. So the least squares approach is going to minimize this RSS. The solution to this has a closed form solution, and you can find this closed form solution all over the internet. It's on Wikipedia. We've known about this closed form solution. It's probably one of the earliest things discovered in modern mathematics. It's very cool. I'm not going to go into it here. So the method of least squares is going to be minimizing this RSS.